Welcome to an extraordinary scientific journey that began in the humble mango orchards of Southeast Asia and could revolutionize global industrial chemistry. In April 2023, researchers from the University of Malaya and Aalto University in Finland made a discovery that challenges our understanding of sustainable catalysis. What they found in discarded mango leaves wasn't just waste. It was the key to a new generation of catalysts that could replace precious metals worth billions, reduce environmental impact, and create economic opportunities for farmers across the tropics. Join us as we explore how this serendipitous discovery is rewriting the rules of green chemistry and circular economics. Our story begins with Dr. Noor Hidayah Ismail and her team, who were originally investigating something completely different. They were processing mango leaves through hydrothermal treatment, essentially applying pressurized water at temperatures between 160 to 190 degrees Celsius. Their goal? To extract mangiferin, a bioactive compound with pharmaceutical applications. But science often rewards the observant with unexpected treasures. Instead of just finding their target compound, the team noticed something remarkable happening to the leaf material. The hydrothermal treatment, intended merely as a purification step, was transforming the leaf compounds into unique structures with extraordinary properties. What they had stumbled upon was a complex of polyphenols and trace minerals that, when structurally transformed through their novel process, created nanoscale structures capable of catalyzing oxidation reactions at rates comparable to precious metal catalysts, but at a fraction of the environmental and economic cost. When the research team examined their creation under electron microscopy, they discovered something fascinating. These weren't just random organic compounds. They were highly organized hierarchical porous structures with high surface area and abundant active sites. Within these structures, naturally occurring manganese and iron nanoparticles were embedded in a carbon framework derived from the leaf's cellulose and lignin components. This wasn't simple chemistry. It was nature's sophisticated architecture revealed through scientific process. The catalyst's activity comes from a synergistic effect between these metal nanoparticles and nitrogen-containing compounds derived from the leaf proteins. This creates active sites with electron transfer capabilities remarkably similar to those found in certain metalloenzymes, nature's own catalysts that have evolved over millions of years. The team named their discovery MANGOCAT1, and its performance was nothing short of remarkable. It demonstrated 87% efficiency in model oxidation reactions compared to platinum's 92%, but costs less than 5% as much to produce. Even more impressive was its stability, maintaining activity through over 200 reaction cycles without significant degradation, a property rarely seen in bio-derived catalysts. This discovery highlighted a fascinating intersection of traditional knowledge and modern science. Dr. Ismail later explained that in several South Asian traditional medicine systems, mango leaf preparations had been used in processes that, in retrospect, likely leveraged these catalytic properties, particularly in the preparation of certain medicinal compounds requiring oxidative transformations. For centuries, traditional healers had been utilizing chemical properties that modern science is only now beginning to understand. As Dr. Miko Makela from Aalto University noted, what makes this discovery particularly significant is that the catalytic activity doesn't come from a single compound but emerges from the complex structural arrangement created during processing. It's not something we could have rationally designed. This humbling realization reminds us that sometimes, the most sophisticated technologies aren't created in laboratories but discovered in the natural world around us, knowledge that traditional cultures have often preserved through generations. To understand the significance of MANGOCAT1, we need to recognize the problems with current catalyst technology. Industrial catalysis has long relied on platinum, palladium, and rhodium, precious metals with problematic supply chains often involving environmentally destructive mining and geopolitically complex sourcing. These aren't just expensive materials. They represent significant ethical and environmental challenges. The global catalyst market, valued at approximately $35.5 billion in 2022, remains heavily dependent on these materials despite decades of searching for alternatives. Precious metal catalysts typically require energy-intensive recycling processes, and despite these efforts, an estimated 5 to 10% of industrial platinum group metals are lost annually to the environment. This creates a continuous demand for new mining, perpetuating environmental damage. MANGOCAT1 doesn't just offer a cost advantage. It represents a complete paradigm shift. Instead of extracting finite resources from the earth at great environmental cost, it repurposes what would otherwise be waste. The more agricultural waste diverted to catalyst production, the greater the reduction in methane emissions from decomposing biomass, creating a virtuous environmental cycle. Mango cultivation generates approximately 9 million tons of leaf waste annually across tropical and subtropical regions. This biomass is typically burned or left to decompose, creating air pollution or methane emissions, a significant environmental problem that has largely been overlooked. The process developed by the Malaysian Finnish team transforms this liability into an asset. It requires minimal energy input, using temperatures below 200 degrees Celsius and pressures achievable in standard industrial equipment. The entire production chain has been designed to operate without toxic solvents, using only water and ethanol in the extraction and processing phases. The economic implications for agricultural communities are profound. Pilot implementations have begun in Malaysia's Perak state, where a cooperative of small-scale mango farmers has established a processing facility capable of converting 500 kilograms of leaves into catalyst precursor daily. Initial projections suggest farmers could increase annual income by 15 to 20% by selling previously discarded leaves. This creates new revenue streams without requiring additional land, water, or fertilizer, simply by utilizing what was already being produced but discarded. The timing of this discovery is exceptionally fortuitous for regions facing climate-related agricultural challenges. In parts of Southeast Asia where increasing temperatures and changing rainfall patterns have affected mango fruit yields, the ability to derive value from leaves provides economic resilience. This isn't just about creating a new product. It's about creating climate adaptation strategies for vulnerable agricultural communities. The processing facility in Perak employs a modified version of equipment already used for fruit processing, meaning implementation requires relatively modest capital investment. This accessibility is crucial for widespread adoption in developing regions. Environmental life cycle assessments conducted by the research team provide compelling evidence of the climate benefits. Each kilogram of manganese produced prevents approximately 15 kilograms of carbon dioxide equivalent emissions compared to the mining, refining, and application of platinum-based alternatives. When factoring in the avoided emissions from leaf decomposition, the climate benefit increases to nearly 25 kilograms of carbon dioxide equivalent per kilogram of catalyst. This represents a rare win-win scenario where economic development and environmental protection reinforce rather than oppose each other. The research team has identified 4 promising applications where manganese shows particular potential. First, in pharmaceutical manufacturing, specifically in the oxidation steps required for many active pharmaceutical ingredients, where the catalyst selectivity matches or exceeds platinum standards. This could significantly reduce the cost of producing essential medications. Second, in water treatment processes, where the catalyst can break down persistent organic pollutants when activated by visible light, offering a low-energy approach to treating industrial effluent. Third, preliminary tests in fuel cell technologies suggest that the material could replace up to 70% of the platinum currently used in certain designs, potentially making clean energy technologies more affordable and accessible. But perhaps most exciting is the fourth application, which emerged unexpectedly during extended testing. manganese demonstrated significant activity for converting atmospheric carbon dioxide into methanol when coupled with solar energy harvesting systems. While still at laboratory scale, this carbon capture capability could eventually transform the material from merely sustainable to actively regenerative in environmental terms. The materials scientists at Nanyang Technological University in Singapore have already begun developing membrane systems incorporating the catalyst for point-of-use water purification in rural communities, showing how quickly this technology is moving from laboratory to real-world applications. With such promising results, the focus has shifted to scaling production and expanding applications. The research team has secured funding from the European Union's Horizon Europe program to scale production and explore applications in continuous flow chemistry. This manufacturing approach reduces waste and energy consumption compared to batch processes, further enhancing the environmental benefits. The challenge of scaling isn't just technical. It's about creating new supply chains and economic systems that connect agricultural communities with industrial chemistry applications. Teams in Brazil and India have begun applying the same methodology to jackfruit leaves and lychee processing waste, suggesting we may be at the beginning of a broader revolution in bio-derived catalysis. Each agricultural region has its own abundant waste streams with unique chemical compositions, potentially offering specialized catalytic properties. This diversification is important not just for expanding the technology but for creating resilience in supply chains. Rather than depending on geographically concentrated precious metal reserves, catalysis could become localized, with regions developing catalysts from their own agricultural waste streams. The manganese discovery exemplifies a fundamental shift in how we conceptualize agricultural waste. Rather than viewing these materials as burdens requiring disposal, they increasingly represent untapped resources with complex chemical structures developed through evolutionary processes over millions of years. As Dr. Ismail observed, nature has been optimizing complex chemical structures for millions of years. We're just learning to recognize and repurpose the sophisticated architectures already in what we've been discarding as waste. This perspective aligns with broader movements towards circular economy principles, where the outputs of one process become valuable inputs for another. The mango leaf catalyst represents an exquisite example, transforming a material typically considered worthless into one that enables cleaner, more efficient industrial processes. This shift in thinking has implications far beyond catalysis. Agricultural systems produce enormous quantities of biomass that are not directly consumed as food. Stems, leaves, husks, and processing residues. Historically, these have been treated as waste management problems rather than valuable resources. The manganese story suggests we should be examining these materials not just as bulk commodities for burning or composting, but as sophisticated chemical resources with properties evolved over millions of years. As climate change pressures and resource constraints intensify, innovations at the intersection of traditional agricultural knowledge and cutting-edge materials science may prove increasingly vital. The quiet revolution beginning in mango orchards could reshape how we think about the relationship between agriculture, industry, and environmental sustainability. The manganese story also highlights the value of serendipity in scientific discovery. The research team wasn't looking for a catalyst. They were searching for pharmaceutical compounds. Their willingness to investigate unexpected results rather than considering them experimental failures led to this breakthrough. This reminds us that scientific progress often comes not just from hypothesis-driven research but from curious observation and investigation of anomalies. Looking forward, the principles demonstrated by manganese could extend to numerous other waste streams and applications. Each agricultural product has its own unique biochemical profile that has evolved for specific functions in the plant. These could potentially catalyze different reactions or serve entirely different industrial purposes. We may be at the beginning of a new era where bioprospecting focuses not on finding new organisms, but on finding new uses for the waste streams we already generate in abundance. What began with mango leaves in Malaysia has sparked a global reevaluation of agricultural waste streams. Research initiatives have sprung up across tropical and subtropical regions, examining everything from banana stems to rice husks for similar catalytic properties. The mango leaf catalyst represents just one example of what might become an entirely new class of bio-derived industrial materials. The environmental implications extend far beyond just replacing precious metals. By creating economic incentives to collect and process agricultural waste, these technologies address multiple environmental challenges simultaneously, reducing uncontrolled burning of agricultural residues that contributes to air pollution, preventing methane emissions from decomposing biomass, reducing demand for environmentally destructive mining, and lowering the energy intensity of industrial processes. Perhaps most importantly, this approach creates economic alignment between environmental protection and rural livelihoods. When agricultural waste becomes valuable, proper environmental management becomes profitable. Farmers transition from paying for waste disposal to earning from waste utilization. This economic realignment may prove more powerful than regulations alone in driving sustainable practices. The mango leaf revolution reminds us that sometimes solutions to our most pressing technological challenges may be found not in exotic new materials, but in re-examining what we've been discarding all along. The discovery of manganese represents far more than just another scientific breakthrough. It embodies a fundamental rethinking of our relationship with agricultural systems and industrial chemistry. By transforming mango leaves from waste into valuable catalysts that can replace precious metals, Dr. Ismail and her team have demonstrated how circular economy principles can address multiple challenges simultaneously, reducing environmental impact, creating economic opportunities for farmers, decreasing dependence on problematic mining operations, and making essential chemical processes more sustainable. This paradigm shift extends beyond mangoes to potentially thousands of agricultural waste streams worldwide, each with unique properties evolved over millions of years. As climate change intensifies and resource constraints grow, this intersection of traditional knowledge and cutting-edge science offers a pathway to more resilient, sustainable systems. The quiet revolution beginning in the mango orchards of Malaysia may well represent the future of green chemistry, one where we don't extract new resources from the earth, but instead recognize and harness the sophisticated molecular architectures already abundant in what we've been discarding as waste. In this future, every agricultural region becomes not just a source of food, but a potential source of advanced materials designed by nature itself. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.